This is the system we're going to demonstrate for you today. What it consists of is a DPSS YELF laser, 1047 nanometers. Right now it's running at 100 kilohertz. You can see the display on the scope, and the separation between the rising edge of those pulses is indeed 10 microseconds. It's the laser itself. We have a little ND filter to bring the power down to the level we want to demonstrate with. There's our probe. The probe is connected to the Mach 5 box along with the USB and the power. The analog out is going out to the scope. Then we have our laptop here displaying the application software. This is in live mode. You're looking at a strip chart of the data that's being measured at 100 kilohertz and about 1.2 microjoules of energy. What you're looking at here is the live mode display for Mach 5. While it's still measuring pulses at full 100,000 pulse per second rep rate, and by the way it can measure down to 1 pulse per second. The live mode display, the box is sending data back out at a 10 hertz rate, which is typical of an instrument. Typically 3 hertz, 5 hertz. We have a 10 hertz rep rate. To show you that the data is indeed live, Don's going to put an ND filter in the beam. And you see where he brought the filter in there, and you can see now that the data has dropped, and now it'll come back. So what I'm going to do is I'm going to clear the screen now and start over. And Don's going to drop that same ND filter straight through the beam. And you'll notice you're not really seeing anything. That's because typical of a joule meter that you're going to buy on the market today, they're simply not fast enough on their display update to capture something happening that quickly. You would never know that it happened. We're going to back out of the live mode right now and go to the main display. I can push exit, or I can just click on the exit button. You're looking at the front panel. There are a number of tabs across this panel. We'll go through each one and describe what's going on. Also across the bottom of the screen here, you'll notice all of your main controls that you're going to spend the most time using are always available to you, regardless of which tab you're on as you go through. Those other displays are always there. I'm going to show you one of these right here. This is the data histogram. This is a set that we took earlier. You can see you have the histogram and you have the best Gaussian fit to that curve. This gives you a real good indication of what sort of distribution you've got with your laser, and you can look for oddities going on that you may not see just in a data screen. There's a couple of things going down the side over here. These are check boxes you can turn off and on as you run the data. There's temperature compensation. You can turn that on and the indicator will light up there on the top to let you know. Those indicators are also always visible. You can turn on wavelength correction. You can turn on trigger level tracking. I'm not going to spend a lot of time explaining what those things are because you can always turn on Show Context Help. Put your cursor over that item and it will give you a very complete description of what that is and how it works. I'll turn that off now. You can also always just call the help manual up if you want to. Print that out, keep it by your side if it's something you want to read, but it's going to have descriptions of all the controls, pictures of the software, and what these things do. So there's plenty of help available for you while you're using the software. One of the things that's kind of nice on this is there's a button here called Auto Set. You can push that button, and what's going to happen is the instrument is going to go out and find the correct range and the correct trigger level for the data that you're measuring. This is very useful if you don't really know and you don't have a scope handy. Now you'll notice it went through the system and we now have a trigger light. We are now armed, we're triggered, we can measure data. I'm going to show you something else here. If you should turn the power off on the box, you'll notice this indicator here, USB active and Mach 5 found, your initialization LED, they all turned out and all of your buttons went to sleep. This is because the box is no longer being detected by the software. When you turn the box back on, there's a couple of indicators in the front. They'll turn on full and then one will go out and the other one will go out. When they both go out, that indicates the box has passed its internal self-test. It'll reread the probe EEPROM, and just in case you might have changed the probe EEPROM, maybe while you turn the power off. But now you're back to the front page and all your lights are on and you're ready to go. So what I'm going to do is I'm going to tell the box I want to auto-read the batch and I want to send the data to the displays. You can also send the data out to a data file, or you can send it to both. If you don't tell it to auto-read the batch, you can manually tell it what pulse you want to start at and how many pulses you want to get. So I'm going to go to the strip chart. I'm going to range down to the 2 microjoule range. The auto set left us in the 20. and I'm going to arm the box to get a data set of 300,000 pulses. Now while this is going on, you remember the demonstration we did in the strip chart where Don dropped to the ND filter through the beam? We're going to do that again in here when we're measuring at full speed. You'll see a box come up. Go ahead, Don. And what that box basically means is it stayed there for 3 seconds. The laser's running at 100,000 pulses per second. We told it to get 300,000 pulses. It's now dumping the internal pulse memory to the software on the application. When it gets to 300,000, the data is coming out in a binary format. This box will go away. Another box will pop up that's converting it from binary format to absolute units. And when that box is done, you have your display. Now you see those two little dropouts in there. Is where Don dropped that filter through the beam. So we'll zoom in on that. And I'll change the display option to just be single data points. Now what that is now is you have a little square on the plot everywhere where data existed and no connecting lines. So you can see right here we're measuring along at our 1.2 microjoules, and here's that drop through the beam. This is the edge of the filter occluding the beam. Here's the beam is totally blocked by the edge of the filter. It's coming back out, and there's that same level we saw on our chart when he kept that in the beam constantly. That's the laser being attenuated by the ND filter. Here's the same occlusion as the edges drop out, and we're back to measuring normal data. Just to point out something, this edge here, where the beam is blocked, is longer than this edge here, as indeed it should be because the filter was accelerating as it fell through the beam due to gravity. Now if we go over to the data histogram, it's going to look quite a bit different than the first batch I showed you, which is why I showed you the first batch, because we have all of these low values where the beam was being occluded. We go to the stats page, and we see we have a number of things. We had a minimum of, about 150 nanojoules. So I'm going to come down here, I'm going to change this threshold level to 1 microjoule. That's right. And you'll notice two of the boxes here are dashed out. There's nothing in them yet. These are missing pulse indicators, and we haven't asked it to find them yet. You'll notice also that the average frequency is not quite 100 kilohertz, although it's very close. The reason it's not is because the average frequency is simply the total time it took to gather all of these pulses divided by the number of pulses it gathered. And since we had gaps in the time due to the fact that the beam was blocking them, the average frequency looks lower. So I'm going to go in here and I'm going to ask it to search for missing pulses. And you'll see another box pop up while it's doing that. And I have my threshold set too high. I'm going to have to move in here and change that. Go ahead and cut, Mark. Okay, so now we've searched for missing pulses. And you see now we have numbers in these boxes. We have pulses below a threshold, which I set to 1 microjoule. And we have pulses below the trigger. Pulses below the threshold is fairly straightforward. If you go back to our strip chart, here's my 1 microjoule level. Everything that fell below that 1 microjoule level, all of these pulses, are pulses that were below the threshold and got flagged as missing. It's a very useful feature for searching for runt pulses, especially with an external trigger. Pulses below trigger are pulses that should have been there based on the known frequency of the data, but weren't. And they occur right here. So if your laser is starting and stopping on you and intermittently doing things that cause pulses to drop out, and you take a data set, you can find where that occurred. Because once you tell it to search for the missing pulses, the timestamps in this gap and this gap, here and here, where pulses should have been and weren't, are going to be recorded right here in this array. And there will be as many entries in that array as there were pulses that were missing. I'm going to go over to the FFT tab, and we'll zoom in on the front edge. If you remember what that strip chart looked like, basically we put a little square pulse in the data. And if you can think back to your signals and systems days, the Fourier transform of a square pulse is a sine of x over x function, or a sinc function. It's this characteristic decreasing amplitude pumps, so to speak, that go on out to infinity. Sure enough, here they are. It's very useful for finding periodic or non-pure